I'm at Arsenault. I'm the maintainer of the AMD GPU backend and llvm-reduce, and today I'm going to talk about how to reduce middle-end and back-end bugs in llvm. So because, of course, LLVM never has any bugs, I've arranged some demonstration bugs in a plugin pass that you can find on my GitHub. I got this to work on Linux if you enable the shared libraries build, which matches the Ubuntu package defaults. It does not match the default project build default. It almost works on Mac, and plugins don't work on Windows. So, you just use like any other plugin. Use the -load pass plugin option to opt, or -f pass plugin to clang. There's a bunch of named parameters, like any other pass in the new pass manager, for bugs to enable. I couldn't figure how to make that good with the full pass pipeline, so there's just an environment variable you can set to set things through clang for the full pass pipeline. If you build this plugin or build my repository, it will generate most of the example scripts in this talk with all the paths set for your build, so you can just run them directly. So for this example, I'm going to try inducing a crash in llvm itself. So I picked x86 isolowering.cpp. It's everyone's favorite file. It's one of the biggest in the whole project. And I'm going to enable this crash where we're going to crash on a load from an int pointer. So you can just go run ninja-v and then copy and paste the run line on this, add the -f pass plugin, set this environment variable, and it should get this crash. So clang, depending on your build settings, clang will produce this error. It will give you this, here's your configuration information, and generate this generated reproducer script in C++ file, which is helpful for bug reports. If you don't want to reduce a bug yourself, this is a helpful starting point for maintainers. In this example, it's not hermetic because the bug's actually in this plugin, which is not included in the reproducer, but that's generally not an issue. This is where you would start if you were debugging a front-end issue. You would use one of the C reduction tools, for example, cvise, but I'm not going to cover that in this talk. So the first step is you need to figure out where the crash occurred, and you want to get that into a self-contained IR command that reproduces the failure. And you get the best results if you can get that reproduction command down to a single pass run. And it usually works out all right to just take the IR at the failing point, at the failing pass, extract the IR right before it, and run. This is one of the benefits of a modular compiler IR. If you repeat the process as you refine your test case. Some failures are super sensitive to the exact state of the compilation at that moment, like anything in the register allocation pipeline, and you may need to work harder to reproduce. So in the easy case, the backtrace will just tell you exactly the pass that ran. See, it told us, buggy pass with this option failed on the function. Okay, so in this example, that's enough. So we can go straight to the IR at the point of failure. And this is the happy path, which usually works. And then you run the singular pass with opt. Or if it's harder, you can try to reproduce this invocation as closely as possible from the start. There are still things that are not captured in the IR that are only captured in the global command line options that are set in clang. And things are a lot easier once we get to a single reproducer. If you need to do this, you're running into some kind of infrastructure issue that we should probably address. So the first thing you need to do is to tame the original clang output. You have to add the -emit llvm option onto clang to change the output format from the default object or text assembly. And you also need to add the disable llvm passes flag prefixed with -x clang. And it's important to note that do not think to go touch the -o flag. Sometimes people want to go remove 03, and they think 00 is synonymous with running those no passes. This is not correct. These are orthogonal settings. Clang produces different IR at 00, and 00 does not mean run no passes. So you just want to add this one flag and then change the output format, and then you've got the original IR that clang produced. You can redirect that output by changing the -o flag that was in the original build into some file you can work with. And now with some bit code, you're ready to use opt. So in the GitHub, it generates this buggy op script, which just passes the plugin. You run O2. And you can optionally add this disable output flag, which will just, not avoid printing useless output, which, can help speed up and not print so much spam to your terminal as you're reducing. Another thing to note is opt02 is a close but imperfect approximation for whatever Clang was originally doing. This is a lot better than it used to be, where the past pipelines were slightly different. But today, at least on x86, though they do seem to be the same, modulo any compiler flags, as I mentioned before. And of course, it's also possible the failure could be in the output, although that's uncommon, in which case you need to get rid of the disable output. So in the easy case, to extract the IR right before the crashing command, we have the brute force approach, which is called print before all. This will print the IR unit before each function or loop or module that it's printing. And it's a really low-tech solution, and it prints out something that looks like this. You probably don't get the syntax highlighting, but it's just like comment and then IR unit at that point. But this is not actually usable in any tool. Like, for example, a function pass only prints the function, but that's not useful because there's always going to be something in the module scope that you depend on. Like, almost all instructions are going to have like metadata like these metadata references are printed at the end of the module. So there's an additional flag you need to use that's just way too much text to work with, and it's not even enough. You still need the print module scope flag to have something that's parsable. And this is really impractical. For example, on x86 ISO lowering, if you do print before all, I gave up after waiting an hour and had over a gigabyte of text output, and it wasn't anywhere near the crash point. So we need some filtration, which we have a few different tools to help us with. So we have print before, which is just the same thing, except it filters to before a specific pass. And we can, take the name out of, our helpful crash log before, and just you don't need the pass parameters. You just take the buggy part. That should work. You can also print relative to the next pass, so print after the previous pass or print before, print after the last pass that ran. In our crash log we had this, so just as well you can take, print after lower constant intrinsics, it's the same thing. Of course, you can take all these flags to opt and just put them to Clang too if you want to. You can use Clang or opt pretty much interchangeably. You just have to prefix them with -llvm with Clang. And we have this other one I basically used to just filter it on a specific function, but then you have to take this gigantic mangled thing and figure out what that is, and that's no fun. So the best, most reliable way to do this is to use print before pass number. Another problem with using print before is the same pass can run multiple times, and print before or print after just gets every instance of that. If you want the specific instance you crashed, you want print the exact pass number. So if we use print pass numbers, we get all this output, but it tells us exactly what number we need to print just that one instance. So in this example, it crashed on the 466,784th pass run. So now we can take that number, put that into print before pass number, and now we have almost usable IR. If we redirect std_error to a file, we have the raw std_error output, which is all the IR we want with a comment, plus some junk at the end from the backtrace and the errors. You have to go into the file and manually trim that off to get something parsable, but that's easy. But there's a better way now. Since 2023, we have this new IR dump directory option. So that just prints it to a file without the extra std_error stuff you don't want. So then you have directly usable output. So it's easy to use. You just give it a directory, and it will put some hashes, the pass number, and then the pass name and some other junk. It works in composition with all the other print flags, so you can just get accumulate a direct refill of these different temporary files. And you can directly use those. But it turns out it did not work with print vast number correctly when I tried to make these slides, so I had to fix that. So it works. This works better now. And now we have this big, giant 1.1 million line test case that's really scary, but we can use llvm-reduce to make it manageable to debug. So llvm-reduce will handle most of the reduction process for us. It is an IR to IR text or bitcode to bitcode reproducer. It tries to, by default, it tries to reduce to the original format it had. So you give it text IR, it will pass text IR to the tool you're using, and then produce a text output. It works best if you get a minimal set of minimal reproduction command, but you can actually just put whatever you want as long as the failure reproduces on a bitcode input. The API is quite simple. You create what it calls an interestingness script with your IR reproducer command. The script has a very simple API. An exit value of 0 is considered interesting. It expects to receive one argument from the input file name and exit 0 or non-zero. It can be any program, but it's usually simplest to use bash. If you want, you can use Python or whatever you want. llvm-reduce will also forward along any other arguments fast with -test-arg, but it's common to need that. This exit value is unfortunately backwards from what you would hope for a crash, but it does match grep or file check, which is kind of handy too. So here we have our interesting script, which is just run opt with our plugin, and then run the pass we have, and we have to make sure to invert the error code and forward along the arguments from the script. Make sure you don't forget your shebang line, or else you get like some stupid POSIX spawn error. And don't forget chmodx either. And then you'll probably want to redirect std_error to dev null, or else you'll get a lot of spam printing as you reduce. You should also make sure to write this to be multiprocess safe, which mostly means be careful about temporary files. Use maketemp to get a proper global unique file. So now we're ready to actually do the reduction. And it will do its thing. It will print some basic status information about the reductions it's using. It has a whole bunch of reductions it does. This one doesn't take so long. It takes about, this test took about 30 seconds to reduce. The time it takes is more of a function of the complexity of the reproduction. It's more of a function of how complex your reduction conditions are rather than the size of the test case. And it reduced. So we look at what it got, and we got this thing after about 30 seconds. So we got this 15-line reproducer out of our 1.1 million line original test case. But if you look at this, it has some peculiarities. It has this, it found the failure in unreachable code, but the original failure wasn't in unreachable code. It also found this thing that instant reply would have replaced with a constant null. It's debuggable, so it helped us, and now we could actually do something with that. You can get away with any bitcode reproducer, as I mentioned before. But you do get better results with just a single pass. So in this case, on the left here, this is what you get if you run it with opt02, and on the right is if you bothered to get it down to the single pass invocation. The single pass invocation took about 30 seconds. Running the full O2 made it take about 2 minutes. And we ended up with this bigger thing that was hidden behind some function calls. The inlighter made this more difficult. I actually have a pull request open that gets these down to like the same output. But this is what you got when I made the slides. If you don't like that weird result, you can always adjust your interesting script to filter out unwanted results. So if we prune that output with insimplify and simplify CFG, we get this nicer looking, more normal output. Although this is a really heavy hammer of a workaround, especially simplify CFG. There's a lot of extra stuff beyond just get rid of unreachable code. And it turns out we don't have a utility pass that only deletes unreachable basic blocks, even though we have 2 utility functions that do the exact same thing. So we can also use this to debug other kinds of situations that aren't crashes, but you need to make them turn to crashes. So if we have a hang, we can adjust our interesting script to add something like the timeout command to turn into a hard failure. This is obviously an imperfect system. You need to make up a number. It's some arbitrary threshold. You might not be certain that it's actually an infinite loop or if it's just taking a really long time. And the timeout is going to artificially pad out your reduction time. So if, in this example, I created a bug of infinite looping on an indirect call, and reducing this took about 30 minutes compared to the 3 seconds in the simple crash. And in this case, we also ended up with a funny reproducer in unreachable code with an undefined call to null. But we can rerun this interesting script with the basic cleanups again as the trick to make this look nicer, and we get what we actually what the bug was intended to debug on. Believe it or not, compiler passes can actually have multiple bugs in them at the same time. So we're going to try now turning on multiple bugs in the buggy crash pass. So if we turn on these 2 bugs, we're going to make it contextually dependent on when the bugs can happen, and we're going to turn on 2 of them. In this case, we're going to crash if it's inside a function with internal linkage. And if we put this on the x86 ISO lowering example we extracted earlier, it happens to hit this first bug where it breaks on I1 typed selects. And if we take this and then run it through llvm-reduce again, and then we take our interesting script again and run it on that, surprise, llvm-reduce found a different bug that wasn't the one you were looking for. So it was you got a bonus bug, llvm-reduce acted like a fuzzer and found something else broken for you. So the good citizen thing to do at this point is to go fix this other bug first, or file it for later so somebody can fix this, because it does find useful things like this. But if you want to just plow through and debug the original thing you're looking at, you can adjust your interesting script to filter that out. The way you usually do this is just by refining your error condition on whatever gets printed to std_error. So we have to remove the inverted exit code, then we pipe it to grep, and then as mentioned before, the entering this exit condition matches grep. So if we grep for the error log for the error message and remove the inverted condition code, now we're looking specifically for this problem. And use grep-q to reduce the amount of printing spam that happens while it reduces. And then we can run that through, and we get this reduce test case, which finds the correct failure. You can also, if you don't want to depend on a system tool, you can redo the same thing with file check, and you get the identical results. So llvm-reduce also has a whole lot of options. Sometimes you need more control to reduce successfully. Some reductions may be counterproductive to your bug. You can also use the options to work around llvm-reduce bugs. So first we have this print delta passes option, which will just print all the list of reductions it does. Also, it prints the names of them as it's doing the reduction. So if something breaks, you can see which one it was and then turn that one off. It's also not useful to run llvm-reduce repeatedly. It already does that itself while the test case is still changing up to some number of iterations. I think by default it does 5. We have a way to opt in and opt out of specific reduction techniques. If you use the -- delta passes flag, it's just a comma-separated list of the reductions, and you can extract the name from the print delta passes flag or the status. More often than not, I find it useful to disable specific reduction passes. For example, one I routinely disable is the attribute reduction, because in my example, I know it's going to be counterproductive. For example, on AIM GPU, we have a lot of attributes that change the registrar allocation budget, which has radical impact on code gen. So it's almost certainly going to hide any kind of code gen bug I'm debugging. So I usually turn that one off. Another interesting one you might want to skip is one of the reductions it does runs a pass pipeline with some IR passes, but that's obviously a problem. If the problem you're reducing is in one of those passes, llvm-reduce is just going to blow up on that. So it can use skip delta passes to avoid that one too. Or you can restrict that to running specific passes. It's just another option to the IR passes reduction. So you can make that just run SROA and not the others it does, for example. llvm-reduce also has a variety of more mechanical options. We do have the parallel enable or disable option for the number of threads. This does happen to work around some bugs. It also does, by default, try to do everything in terms of the original input format, but we also have this write temp files as bitcode, which can work around some other bugs. We also have this other option, which cuts down the number of times introducing the script runs slightly at the expense of you lose a warning that your test case is flaky. If you do have a flaky test case, it should get you somewhere, but it will be less reliable. You might need to do more in that case. There's also this abort unvalid reduction flag, which is more useful for debugging llvm-reduce itself. We ideally would not have any invalid reductions. It adds steps to the algorithm, and it just wastes time. And it's potentially represents missed reduction opportunities, so it's interesting to file bugs if anything errors on that. There's also this preserve debug environment flag. By default, llvm-reduce disables some debug features that LVM support library enables by default, namely llvm disable crash report and llvm disable symbolization. Both of those are really slow, and they slow down your reduction, so it turns those off by default. But you can force those to be on if you want. So one thing I glossed over in the original example was the usage of Clang at the very beginning. So for those who don't know, Clang actually functions as two programs. The interface you interact with usually is called the Clang driver. It functions to build a sequence of commands, which most frequently means run Clang itself with the -UC1 argument to perform the actual compilation. Clang reinvokes itself with some translated arguments, and then the real compilation is the reinvocation. In this basic case, there's no linking, and there's only one step, so it's simple. You can inspect what the Clang driver is doing with the --# argument. One annoying thing is Zish doesn't like this argument for some reason, so you need to quote it, but you don't need to quote it with bash. In more complex cases, you need to understand what your toolchain is doing. So with LTO, for example, the steps change, so the Clang CC1s are emitting bitcode and not IR, and then the arguments you gave to Clang may not make it to the right place. The other handy flag for debugging the invocation is -save temps, which saves out the intermediate steps of the compilation. You can quite often just take the bitcode files directly out of save temps and reproduce, but this doesn't always work. For example, your MLVM flags you may have been using might not make it to the right, may not make it to the backend if you're using LTO, for example. If you want additional flags to the linker, there's the -WL prefix you need to add. And then with LTO, there's also WL-plugin opt, which includes another level of save temps embedded in it. So for example, if you want an LLVM flag to debug the backend, -m-LLVM print before prolog epilogue in this example, it won't make it to the backend. You need to prefix it to make sure it gets past the linker phase. So often the most annoying part of getting the reproduction command is just figuring out what the toolchain is doing, because we kind of have a bunch of them that are all just slightly different in annoying ways. But if you just use save temps, there's guesswork, so you kind of need to, you've lost context. If you just have like the files out of it, you don't have the full context. So you need to use this in conjunction with --# to see what it's doing. If you use Clang-V, it also is basically the same thing. It combines those two. But one hazard to be aware of that hopefully doesn't matter is if you use save temps, the steps are actually slightly different than without save temps. Like it introduces this synthetic step. For example, in the C compile case, it introduces this artificial step of preprocessing the file, and then it compiles that file. This usually works out okay, but in the past there have been bugs where these aren't exactly the same thing. So just the implementation to be aware of if things don't reproduce. Sometimes there can be issues in this area. But yeah, in this kind of case, if you're using like LTO, in the save temps case, your second invocation of Clang will be probably where your failure is. And of course, I need to talk about offload languages. So if we compile a test case with OpenMP with --offload arch, and we look at the driver commands, it's more complicated. In offload languages, the tool chain is a lot more complicated. There are more steps, and it can be annoying to get bitcode reproducers. The compilation is performed 2 or more times for each offload target. And then a lot of the actual work goes on in some magic helper tools, which makes the process a bit more opaque. For OpenMP, it's using this new driver where a lot of the work goes on in this tool called Clang Linker Wrapper, which has, very similar to the LTO case, because it's also another LTO wrapper, it's hiding a lot of compilation steps behind yet another driver. In these cases, you need to split your case into, you need to run ### save temps, run those as script steps, then after your final Clang Linker Wrapper tool, you have to run that again, and now you have what you actually can work with. So here is a greatly trimmed for space version. With save temps, the number of steps increases from 5 to 9. And you need to, understand what it's doing sometimes. For example, one important case is here we have some runtime bitcode libraries that get injected into the source program. If you just take the temporary file before that and run, it will not work. You need to make sure this is linked in the right place. HIP, for example, is using an older driver setup where it isn't using the linker wrapper and it directly has the LD invocation. And historically, that has had more bugs where the save temps result isn't identical to the non-save temps path. So yeah, the tool chain can be a pain. You need to be aware of what your tool chain is doing to actually make use of the temporary files. Yeah, so yeah, there's another level of save temps inside the linker wrapper. Okay, so so far we've only been talking about problems that reproduce with a single pass, but sometimes you have passes failures that reproduce depend on your compilation state in bad ways, such that running the single pass in isolation doesn't reproduce. Suppose we have this buggy code, which is doing something with a static variable, which is not in the IR. This is bad. You should not do this. If you want to do something if you want to make some transform, it should be captured in the IR in some way. A more common realistic example why this would happen is incorrect analysis pass management. You didn't invalidate something or something was updated incorrectly. But we have this utility script that can help you out with this kind of case to reduce the pass pipeline list that you would then feed into llvm-reduce. So the script is easy to use. You just point it to opt, give it your arguments, which in this case includes the plugin, give it your Clang extracted output, and then give it the default pass pipeline. Then the output looks something like this. It keeps running the pass until it breaks, and then trims down the pass list. So in this case, we required 2 passes to reproduce the failure. We run this pre-module pass, or this pre-pass that set the flag, and the later function pass crashes on it. This was kind of slow when I tried it. This took 45 minutes compared to the 30 seconds when I just went straight to the failure pass. So it's a lot nicer if you can just run a single pass. And it gave us our minimal pass reproducer. And then these two, we can take this pass as run, put it into our introducing the script, and the output it had with llvm-reduce, and then this is a pre-step to using llvm-reduce. Yeah, so if we do that and we sanity check it, llvm-reduce finds us a single function because the actual code didn't depend on the function. It just needed there to be a function. And now for backend issues, which is what I spend most of my time actually dealing with, you just do all the same things. Debugging anything in the code gen layer is just a second phase of the process. For anything in selection DAG, you cannot do any better than an IR reproducer. You want to ideally get a reproducer command using LLC, but sometimes Clang works just as well. There's a lot of junk in target options that you kind of need to use Clang from the beginning to get it to reproduce. And everything is just generally worse in the back end. It's just harder. The infrastructure is worse. The modularity starts to break down. There's fixed pass orders. CodeGen is still using legacy pass manager, so there's a bunch of arbitrary differences there, and it's harder to debug. Usually just taking clang-03 or 02 or whatever, taking that bitcode and running through LLC, that works. That is pretty reliable, especially for anything like selection tag related. But it's less reliable than running a single pass IR failure in the middle end. For the entering the script, it's basically the same thing, except LLC instead of opt. The arguments are slightly different, the behavior is slightly different. For example, opt has the disable output flag, but LLC, the canonical disable output way is to set the file type to null. But the default output format for Clang is also object. LLC is text assembly. So if you have an emission-related problem, you might need to change the file type to object or ASM. Another handy thing to do is turn on the machine verifier. This is default in expensive checks builds, but it can find useful things while it's reducing if you turn it on, but it can be prohibitively expensive for a big enough test case. Another thing to be aware of is there are IR passes that run on the code-gen pipeline. There are additional IR optimizations that are repeated in the middle end, and these extra cleanups can complicate reductions and getting to minimal test cases. It is possible to use start after or stop before, or start after to skip these extra passes, but this infrastructure isn't great. Not all passes can or should be skipped, but nothing stops you from skipping them. So if you skip the wrong thing, you might just blow up on something else later, and that's unhelpful. Yeah, and verified machine inserts can be helpful. Since CodeGen is still in the legacy pass manager, the debugging features are different. We no longer have like the print pipeline passes option for opt. We have this older thing called debug pass. I usually look at debug pass equals structure. It just prints out these like casual names, the descriptions of the passes. We don't have the most consistent naming scheme for these passes. For example, one that plagues me is prolog epilogue inserter. The name printed in like the debug log, and the name of the class, the name of the file, and the name of the name you can actually refer to in the pass list are all different, and they're not consistent on it being kebab case or whether it has a UE at the end. So hopefully, with the move to new pass manager, we might have an opportunity to clean this up and have some consistently usable names. So there isn't really a better way to like figure out how to name the pass than go look at the code for what it defines its debug type as. If you get into like later middle end issues after like selection tag, llvm-reduce does support Mir, but it's still quite rough. I gave a talk about this about 3 years ago, and very little's changed. The Mir structure could use a lot of improvement. It needs a lot more TLC than it gets. Targets need to implement custom support for their custom machine function info fields and so forth. And almost every I don't think any target has 100% coverage there. There's still generic stuff that's missing. We're missing things like the IR has the support to track the useless order for a value. The moral equivalent in Mir is the register useless, but we don't have any representation for that. So a lot gets lost in the serialization process. So we're missing a lot of reduction techniques in Mir. Most notably, we're missing any of the control flow reductions. It also does not have useful liveness tracking, so it just hacks stuff out and sees the machine verifier fails, and it does not work well. It needs to be more intelligent than that to produce more usable test cases. So to sanity check if you can even reproduce a failure with Mir, you can stop the compilation process right after the initial selection and legalization, and then try to resume the rest of the CodeGen pipeline before then. So if you run finalize ISL, take that Mir, and then start after finalize ISL, if this reproduces for you, you can probably do better. But this will sanity check if you're running into like the most basic of serialization issues. If you really, really need to, like I sometimes do, you can skip ahead to this process and just dump to Mir straight from Clang. You can just add all the same flags, stop before the machine pass from the original Clang invocation. I often have to do that with the register allocation pipeline, and here are some handy points that I often make use of. The start of the process is fee node elimination, then the coalescer, the machine scheduler, and greedy. The machine scheduler in particular is a useful point because there are some like weird side effects that happen in live intervals that the machine scheduler sort of perturbs, and then there's like side state that isn't captured anywhere that is relevant later on in the process. So here are just some sample mere interestingness scripts. It's basically the same thing. It's just LLC. Then you might want to use some of these, your past pipeline selection. You can specifically override the input with the -x flag. We have more refined versions of the verifier, like verify red-jalloc is more targeted. It might be more practical if you want to reduce with that rather than verify machine insters. Yeah, you can also just run a single pass at a time. Okay, so not all problems are directly manifest in the compiler. So if you're debugging a miscompile, good luck. This is more of a function of debugging your program and not the compiler. The compiler does not have magic insights into your miscompilation. You should also, do the basic due diligence to make sure there is actually a compiler bug. Use your sanitizers first if possible. We also have this utility lint pass that can report on some obviously undefined behavior in the IR, although I would say this pass is kind of forgotten and it does about 5% of what it could. Getting to any kind of pass-fail diff is extremely useful. Once you have some kind of, I know this is good, this is bad, you have some traction to look at. It's very good. Trying to execute misbehaving code in an llvm-reduce interestingness script is probably not that useful. We could consider introducing a mode where it tries to maintain executable behavior, but I'm not sure it can do that much. We have like maybe 3 or 4 reductions that will actually be behavior preserving now, just like the drop annotations and so forth. All the reductions that just strip optimization hints are the only kind of reductions that it does that will maybe be useful here. More potentially interesting is, once you've identified some interestingness diff, you can use llvm diff in your interestingness script to get like a minimal example of whatever you noticed in the diff. Also useful here is we have this opt bisect flag. It's just sort of pass manager magic to trim, to filter out passes that aren't strictly required. You can just add the opt bisect limit flag to any tool that runs passes. If you run it with the -1 argument, you will print out this. Okay, so in this example, we're going to try debugging this miscompile. We're going to have this program, simple program that just returns if the number of arguments is less than 2, and we're going to miscompile this into an off by 1. So if we miscompile this compared to 2, we'll see an exit 1, but 2 is not less than 2, and it should be, so it should exit 0. So if you run this miscompile and run script with the bisect limit of -1, we'll see there are 142 optional runs of passes. So now we can take that number, we can run with -mllvm opt bisect limit equals 0, which is approximately skip all optional passes, and then we see that we got the correct exit value of 0. And if we start, moving that value up and down by section pattern, we'll see eventually we get down to, we do that like 6 times, and then we find the problem manifests only after running past 70. So it found the bug. Now, I will say that this is not definitive proof the bug is in this pass. I would say about half the time I've used this successfully, the actual bug was manifest somewhere later in the pipeline. It just happens to have broken on a pattern introduced by this upstream pass of it. But at least this gets you to a smaller diff you can work with, a pass-fail diff you can inspect. We have some miscellaneous tools that can be useful for jump-starting this process or perhaps using in your interestingness scripts. For example, if you have a case that's really, really big and takes a really long time to compile, you can get a jump start on the process with llvm extract. If you know the problematic function, you can extract that function and use the recursive argument to get all of its dependencies, and that can save some time in the initial reduction. You can also extract specific basic blocks from functions, and you can use llvm diff to get instead of just regular diff. We also have this normalize utility pass, which is intended to shuffle code around and name things such that you have smaller diffs. So you can combine these, you can use these in conjunction with each other to have some more creative, interesting scripts, to find like actual semantic diffs in your reduction. And at the end of this process, you should commit this as a test case in your patch to fix the bug. So we have these other utility passes, which are strip, instanamer, and meta renamer. These can sanitize some of the names and get rid of some messiness. And also for tests, we prefer you to avoid undefined behavior that is unnecessary. If your undefined behavior was not necessary for the bug, you should replace it and verify that your problem still reproduces. For example, most commonly, almost every load llvm-reduce will print out will be a load from a null pointer, which is undefined. You should try to fill that with something else as long as it still reproduces the problem. So here's just a cheat sheet of some handy options. Most every flag works with every LVM tool. Then we have the awkward separation between old and new pass manager when you enter code gen. So llvm-reduce does have some bugs, it turns out. The most annoying one, I'd say, is this useless order bug. It's more of an IR bug. You can work around it by using bitcode only input. It happens to only be a problem with text IR because the bitcode reader and the text ASM parser have different behavior when useless orders don't match. There's also this error, it used to be an assert. I recently downgraded it to a warning that the input module is no longer interesting after counting chunks. This could be a llvm-reduce bug, or it can be symptomatic of your flaky test case, as it will tell you. Also, anything that breaks with abort unveil of reduction is interesting. I'm interested in any kind of cases that hit that. And there's too many bugs to count in Mir. I'm not convinced the multi-threading works correctly with Mir, and we don't have basics like control flow reductions. But if you do hit a bug in llvm-reduce, you know what to do. Like we did earlier in the talk, we can of course reduce bugs in llvm-reduce with llvm-reduce. So here, I wrote this interesting script to debug the issue we had in the first example, where we produced a reproducer in unreachable code. So here's an interestingness script that actually depends on the output. You often have to have filters like you often have to have silly filters like this to make sure we have didn't delete the whole program. We want to make sure there's no unreachable code, so but we need there to be at least one function, so we have to filter there's at least one function. The ASM printer happens to print this handy no predecessor comment, so we rely on that. We need a temporary file, so we can check the output. We disable the unreachable basic blocks reduction because the problem is relevant to basic blocks. We don't want to delete those. I added this special exit code so we can filter out cases where the failure stopped reproducing in the original input. And then we're actually looking for this case at the end where there's no predecessors in the unreachable code. So if we take this and run this on our original input, we find that the unreachable code happened when we had a branch on a constant false. So we can now replace our interestingness condition with one based on file check, and now we have a test case for the actual patch. So I fixed this one, a couple weeks ago, and now you get the original example now gets you what you would want to, where it's only the two instructions that should fail. We have this. If you have any other reduction suggestions, we have the llvm-reduce label on GitHub, and okay, that's it, I guess.
My turn. Thank you for that talk. I think that's one of the talks that receives most empathy because I kind of share the pain that you are sharing with all that knowledge. My question is, so it seems that we have a lot of tools, but do we have a way how we can describe what to do in these cases, or maybe incorporate that knowledge into a tool?
I think it would be hard. There's a lot of there's more art than science in a lot of reductions. The crashes are easy, but like anything beyond that is requires more creativity. I'm not sure how to capture that. I mean, we could have a more streamlined process in some of these cases. I do think that it's kind of annoying the split to code gen, like it's a separate thing. Like in theory, we could have like an integrated thing that just goes straight to the thing, straight to the process. But yeah.
Because I think one of the advantages of having something like a prescription, at least in a GitHub, like somewhere markdown even, is that novice people can get oriented. Because I find myself often describing all these, well, some of these steps to my colleagues, and it depends on how quickly they are with all these things to grasp. And it just that knowledge requires like a lot of effort into and everyday like experience with this, so that you can get it to the point where it's really efficient.
Yeah. You could also always skip a lot of steps. You can always set a breakpoint and then dump the IR at that point, and that might work too. There's many ways to get this done. There's a lot of context dependent. Like I only covered Clang, but any front end needs to have some kind of system. Like the annoying part is usually dealing with the tool chain. Like if you're using some kind of runtime compilation system, they don't always implement something for the poor compiler engineers should work with.
As long as we cover the basics, I think that would be good enough for all these things that we saw already in the presentation.
Yeah.
Thank you.
Any additional questions? Then.
So I will always have had this confusion. What exactly is the difference between when you get the IR from save temps and when you get the IR from emit LLVM?
Well, there are multiple phases of bitcode, but in principle, well, there is a point where they are the same, and then there might not be, but it depends on the tool chain. Like we have a bunch of different tool chains. They all have slightly different behavior, depending on where you're using save temps or not. But yeah, in principle, one of those bitcode files is just the one you want.
I see. So if I want to reduce an IR bug, should I just stick to one of these flags?
I would say the most. Actually, I feel like I blanked out on saying this part. If you run ---- dash save temps, that's pretty much just a good to go reproducer script. If you run that in sequence, it will produce the files, and then one of those commands will fail, and you just take that one, and that's pretty much usable straight as your interesting script.
Okay, thank you, and thank you for the talk.
You can just be a little bit more refined at that point if you want to.
We have 2 more minutes, yeah.
Do you have experience with multi-file reductions?
No, not really.
Let's thank the speaker again.